Before I start, maybe I should note that there are some simplification in the slides compared to the paper. So for full details, see the paper. Yeah, let's start with what is this actually about. You see the title. Maybe let's start with the camera calibration part. Today, the prevalent method to camera calibration is Zhang's method, which uses planar calibration targets, which probably all of you know. And examples for this are the MATLAB toolbox, OpenCV, and the robot operating system. What all these toolboxes have in common is that they provide the user some kind of feedback about the data captured so far, like the per view error or the screen coverage. However, what these methods fall short at is answering the following question, where to place the pattern next. And this is the focus of our work. There's a related work which actually tackles this question already, and this is April by Richardson et al. And what you see here is the method in action. The wireframe display is the target pose, and the user is now supposed to match it with the real target. So how did they arrive at this suggestion? Basically, they have a fixed set of 60 uniformly distributed poses in the view space. And for each of these poses, they generate a synthetic measurement, add it to the calibration set, and recalibrate. And then guide the user to the pose which has the minimal error. So basically, this is just an exhaustive search, only using 60 sampling points. This is because calibration has to perform 60 times, and it's quite involved, so it takes them between 1 and 2 seconds to generate a new pose suggestion. Our approach, on the other hand, tries to explicitly exploit the geometric properties of the camera calibration problem. And we also relate poses to explicit constraints on the parameters we try to estimate. This allows us to analytically generate the pose sequence, and this is much faster. It only takes around 100 milliseconds to generate a pose suggestion. This is also like the outline for the remains of the talk, and we continue with the geometric properties. So think of the Pinhole camera model we use, and let's turn it into a calibration problem. For this, we assume a planar calibration target. So let's say the guy on the left is a cardboard cutout, and Zhang's method now tries to simultaneously estimate the intrinsic properties, which are simplified by the focal length f, and the pattern pose, which is again simplified to the distance z. Also, for the sake of the experiment, assume that the pattern is parallel to the image plane. To let this thing estimate something, let's say we have a slightly smaller image. So to explain this, there are two possibilities, and they are equally probable. The first one is that the pattern is further away, and the second one is that the focal length is a little bit shorter. I'll toggle between them, and which of them is selected is basically random or depends on image noise, because this is an ambiguity in the camera model. Also so-called singularity, and we want to avoid something like this, and to do so we have observed some rules. First of all, the pattern must not be parallel to the image plane. If we observe this, we have perspective shortening, and this can resolve this ambiguity. Also, the pattern must not be coplanar in any two views, because it doesn't add any information. But instead, we should maximize the angular spread. What I mean by this is the number of rotations between the image plane and the target plane. I just leave the claims as is on the slide. Instead, I refer you to the work by Sturm and Maybank, which is cited in the footnote, which specifically refer to the singularities. For now, let's continue to the camera model, or the mathematical formulation of it. We have a projection function pi, which takes the camera pose, which is colored purple here, and some parameters, which are colored green, and uses them to project 3D point P. If you look at the right-hand side of the equation, you see everything is linear, and this is what gives rise to the ambiguities. However, the typical camera model is not as simple as that, but instead we want to consider radial and tangential distortions. We add them by introducing the distortion function delta as following. And as you see, the distortion function is applied post-projection. So the only thing it deals with is moving 2D points to other 2D locations. Instead of giving you the equation for distortion function, I just give you the results of the distortion function with some specific parameters. And the color coding here is following. Blue means no distortion, so the point is not shifted, and red means maximal distortion, or shifting. And as you can see, for a consumer camera, which is this based on, the dominant distortion is radial distortion. And now, with calibration, we performed with the task of measuring this function. So now proposal here is to put as many sampling points as we can in the region where something happens. For instance, the top lower corner. And I would argue that this is a quite good position, because radial distortion is radially symmetric around the principal point, and tangential distortion is also symmetric around the image axis. So by looking in one corner, we can estimate both of them. But let's keep this a claim for now and continue on how to verify this. For this, we want to measure the parameter uncertainty. And to do so, we employ the backward covariance transport. Without going too much into detail, it works by assuming some uncertainty on our input data, which are the pixel positions, and it's colored blue here. And then by applying the Jacobian of the projection function, we arrive at the uncertainty of our, or the covariance metrics for the projection parameters. A note here is that the Jacobian is already computed as part of Zhang's method for the nonlinear optimization, so we get it for free. So now that we have a feeling for the parameter uncertainty, let's continue to an experiment. For those who just woke up after the lunch, this may be the most important slide for my talk. So what we see here are on the left the uncertainties for the pinhole parameters, like principal point and focal length, and on the right you see the uncertainties for the radial distortion coefficients. This is measured for calibration after adding in each new frame. So we captured 20 frames in total. And for capturing, well, also I should note that this is a synthetic image, so it's reproducible. For capturing these images, we performed specific motions. It's following. So first we did a parallel shift, so the pattern was parallel to the image plane, and then we started tilting the pattern. And as we would expect, the uncertainty is high as long as the pattern is parallel to the image plane, because as mentioned earlier, the focal length and principal point cannot be reliably estimated. And as soon as we start tilting the pattern, there's a significant drop in uncertainty, and it converges against the final value. For the radial distortion coefficients, on the other hand, there's immediately a strong drop, and the uncertainty stays about the same. Additionally, we reversed the motions, so we started with tilting the pattern and continued with shifting. And again, as we would expect, we are tilting, so we have some parallel, so perspective shortening, and can estimate the intrinsic or pinhole parameters. For the lower left figure, but what's interesting or remarkable is the lower right figure. As long as we're tilting, the uncertainty for the radial distortion parameters stay high. And only as soon as we start shifting the pattern, it significantly drops. So what the experiment tells us is that we actually need two distinct motions to capture both pinhole and distortion parameters. And based on this experiment, we also derive our actual post-selection scheme, which I introduce you here. So let's assume we are targeting the pinhole parameters. Here we want to maximize the angular spread. And to achieve this, we employ the following binary subdivision scheme. We start with the pink cameras and place two new cameras in the center between two existing, so the yellow ones. And then we propose them to the user, and as soon as he visited both, we can apply again the subdivision scheme to get 4 new cameras, and so on. And as desired, it maximizes the angular spread. For the distortion parameters, on the other hand, as motivated earlier, we aim for the regions with the highest distortion, and also try to put as many sampling points there as possible. Additionally, we remember the regions we already visited and set them to 0. This is indicated by the blue rectangles here. Which of these two schemes gets selected depends on the parameter with the highest uncertainty, which you see in the bar plot on top. What you see there is not the variance, but the variance divided by mean, so we have a similar value range for all parameters. And in this case, our method would aim for the pinhole parameters and the binary subdivision because the uncertainty for the principal point is highest. So given we have a post-selection sequence now, let's make some results, quantitative results. For this, we used the consumer camera at 720p resolution and recorded a separate testing set consisting of 50 images at various distances and angles. And we compared our method to AprilCal, which is obvious, and OpenCV. We used as measure the testing error and the frames required until convergence. Also, there's a training error for completeness, which is also known as a reprojection error. And as you can see, our method arrives at the lowest testing error using the lowest number of frames. The open question now is, okay, it says it just requires 9.4 frames, but is this a minimal solution, or could we leave out some of these frames without compromising calibration quality? So we added a minimality test, which starts with our calibration frames, like 9 frames, and then tries to leave out some of them without reducing the calibration error. The algorithm is in the paper, and I will just give you the results. So the post-selection row is like copied from the slide before, and the test gives us, yes, we can go as low as 7 frames. Which seems like we are doing lots of redundant work, but one explanation for this is that we require 2 additional frames to determine convergence. Our convergence criteria is that the uncertainty doesn't reduce further. So once we converged, actually, we need 1 more frame to determine that we didn't improve. Yeah, so this leads me to the conclusion. Yeah, first of all, maybe probably the amount of frame can be reduced by using some more clever convergence criteria. Then to make this generally applicable, we must consider narrow and wide field of view. Think of a telephoto lens. Then you would need to print out a huge pattern to be able to fulfill the pose suggestions. And this is more of future work. We could also consider additional distortion models beyond radial and tangential distortion. So yeah, here you see our tool in action proposing the poses. If you would like to try this for yourself, the code is on GitHub, and there's also a Linux package available. So thank